In order to calculate torque, we need to change the way we do our free body diagrams a little bit. So let's look at a couple figures here. So in figure A, we have this same hockey stick from before, which is pinned, or it's nailed down at point A here. And in figure B, we have it nailed down at point B. And so you see that when we apply this force F, in figure A, we apply this force F, and because of where it's pinned, it is going to cause some rotation, which is going to be counterclockwise. So we're going to have our torque, which is counterclockwise here, so that is a positive torque. And in B, we have it nailed up at the top, and where our force is in relation to where it's nailed and where it's going to rotate around, we'll have a clockwise rotation, so this would be a negative torque. So the torque here is negative. Now, if we were to say this is in translational equilibrium, meaning that it's not accelerating in the x, y, or z directions, then we would say that in both cases here, both A and B, we'd have our sum of forces in the x direction is equal to 0, and the sum of the forces in the y direction is equal to 0. Even the sum of the forces in the z direction is equal to 0. So this is what we call translational equilibrium. So it is not accelerating in the x, y, or z directions. So translational equilibrium. And so then we would know, since there's one force applied out here, this force F, which is actually applied, it's the same force in both figure A and B. We have that force applied, then there must be another force that is counterbalancing that. So we have, there must be the force the nail exerts on the hockey stick as well. It looks something like this. So in both these cases, the force the nail exerts is, I'll call this Fn for the force of the nail. This is going to be equal magnitude in opposite direction to the force F, such that the sum of the forces in the x direction are 0, and the sum of the forces in the y direction are equal to 0. So if we were to draw a free body diagram of these, then they would look identical, because we would have, if we draw the free body diagram in the way we traditionally have, we just draw a dot, and we have, here is the force F, and then we had, here's the force Fn, which is supposed to be anti-parallel, same magnitude, opposite direction. Then we said, all right, sum of forces in x and y were equal to 0, but we weren't told anything about the torque. So in order to calculate the torque, we need to draw the object at its shape, because remember, torque is, it takes more than just the force into consideration. A torque is that component of the force which is perpendicular to the moment arm times the moment arm. Or we said here, this is Fr sine theta. So we need to take not only the force into consideration, but also how far away that force is. And so if I were to draw the free body diagram essentially the same as the hockey stick here, so this would have to be my free body diagram, then we see that in A we have, well, the distance r. I draw a vector from r to anywhere on the line of action of f, so from r to f, and then the perpendicular component of r would be r times the sine of the angle between them, and so r perpendicular is r sine theta. So the torque in A would be equal to rf sine theta or fr sine theta, either way. Okay, so this is the torque that force F creates about point A. So this is the torque, and this is the way I wrote it like this. Let me write that a little neater. This is the torque about point A, because we have to be careful. If I chose a different point, if I nailed it here, then I would have a different R, and that would be the torque around some other point, call it point C or something. Okay, so I put a little subscript in here so I know it's the torque around point A. So the rotation, if it's fixed at point A, it's going to rotate around point A, and this is how much torque is causing that rotation. Same thing in B over here. If we were just to kind of draw the free body diagram for B, this one looks like this. And so we have this force F applied over here, and here's our point B, like this. And the moment arm was just, this is our line of action of F along here, this green line, and then this is perpendicular already because the force is perpendicular to the surface here. So then our moment arm is just R. We don't have to bother with finding the perpendicular component. It's already perpendicular. And so the torque created around point B would just be equal to RF. Okay? But then we have to be careful with our sign. We need to pay attention to, is this a positive torque or a negative torque, as we identified previously. So the torque at A, this is a positive torque because it's counterclockwise, and in B, this is a negative torque because it's causing a clockwise rotation. So although we have the same force applied, depending on where we're looking at the rotation around, is it around point A or point B, we may have a positive torque or a negative torque. So this leads us to, and we could actually have other forces we apply here. Let's say, well, we'll see this in the next one. But this leads us to the second condition for equilibrium. So the second condition for equilibrium this is really the condition for rotational equilibrium. So this is the condition for rotational equilibrium. Means this condition is that the sum of the torques around any point, I can choose any point I want as long as I find all of my torques around that point. So the sum of the torques around any point must be equal to 0. So this is my second condition for equilibrium. So this allows us to actually throw in yet a third equation when we're solving problems. So now we have, previously we had sum of forces in the x direction were equal to 0. We had sum of forces in the y direction were equal to 0. And now we also have the sum of the torques around any point are equal to 0. So I'll call it any point P are also equal to 0. So now we have 3 equations, so we can have 3 unknowns. Okay, so let's take this problem for instance. So we have, let's say that we have a, okay, so somebody's holding a book, a physics book on their arm here, and let's say that they're holding it in equilibrium. So holding it in equilibrium, we have all of these equilibrium conditions. Sum of forces in the x direction and the y direction are equal to 0, as well as the sum of the torques around any point are equal to 0. So given that we have the mass of the book, and although the book acts over some distance, we'll consider that all of it acts at its center of gravity. So CG stands for center of gravity. Which is the same thing as the center of mass that we discussed previously. So the center of mass. Okay, so we're given the mass of the book, so we can find that force there. We're also given the mass of the arm, so we can find the force of the arm, which also acts at its center of gravity over here, 16 centimeters away. And we are not told what the force of the biceps muscle is or the force of the elbow exerts downwards. And we may not even know the directions, so we just sort of guess directions of the bicep muscle and the elbow. Now, previously what we might have done for a free body diagram would look something like this. And unfortunately, this is not going to give us enough information to solve this, because as I draw my free body diagram this way, I notice here, well, I can find the force of the book, and I can find the force of the arm, the weight of the arm, or actually, sorry, this is the weight of the book, the weight of the arm, but the force of the elbow and the force of the biceps, I don't know either of these. So I have two unknowns, and I'll only have one equation. I can only use sum of forces in the y direction to solve this problem. So we need to use sum of torques as well. So how can we use the sum of the torques around any point to solve this? Well, we note here that in order to have equilibrium, we have the sum of the torques around, in order to have rotational equilibrium, we have the sum of the torques around any point are equal to 0. So we can choose any point that we want to sum our torques around. And so it's most convenient to pick a point in which one of our unknown forces goes through, because after all, torque is a perpendicular force times a distance away. If this distance is equal to 0, then the torque is equal to 0, and we don't have to necessarily include it. So I would like to choose to take, when I'm calculating my sum of torques, I either want to choose this point here or this point here. That way, because I don't know the force of the elbow or the force of the bicep, but the torque created by them, if the torque created by the force of the elbow around this first point would be equal to 0, because the elbow goes right through it. The moment arm is 0. If I take the sum of the torques around this point, then the force or the torque created by the biceps is 0, because the force of the biceps goes right through that point. So we cleverly choose where we would like to take our sum of torques around, and we can get rid of one of our variables that way. So let's see here. Let's take the sum of the torques around this point here. I will just call this point E for where the elbow acts. So the sum of the torques around point E will be equal to, well, force E, I'll put this in here just for completeness. It'll be force E times the moment arm, how far the perpendicular distance from point E to a point on the line of action of E, which is 0. So force E times 0, plus we have, let's see here, force B times that perpendicular distance. Fortunately, these are all perpendicular, so that's just going to be R1. And I have to be careful when I write it in here, is this a positive torque or a negative torque? I see that it's going to cause a counterclockwise rotation, so it'll be a positive torque. And then we will have plus weight A times R2, the perpendicular distance is R2, weight A, and then I look to see what kind of rotation will this cause. Well, this one is going to cause a clockwise rotation, so this is actually plus a negative weight A R2. And then we take a look at weight B, and actually I see here right away it's going to cause a clockwise rotation, so it's going to be a negative torque. So then minus weight B times R3. And in order to have rotational equilibrium, this must all be equal to 0. So we were told the weight of the book. We're given all the distances, so this is all the moment arms here. So we're given R1, R2, R3. We're told the weight of the book. and we were told the weight of the arm as well. The only thing, and this becomes irrelevant because it was multiplied by 0, so the only thing we don't know is the bicep force. So once we use the sum of the torques to find that bicep force, we can then use another equation of equilibrium. The sum of the forces in the y direction is equal to 0. So this means that we have the bicep force minus the weight of the arm minus the weight of the book minus the elbow force is equal to 0. And now that we have the bicep force from the sum of the torques, we're given the weight of the arm, the weight of the book, we can find the force of the elbow. And so typically we'll want to start out by using a sum of torques equals to 0, because this allows us to get rid of one of our unknowns very easily, like we did with the elbow force over here. We could have just as easily decided to do a sum of torques around another point. We could have done the sum of torques around this point here, and we would have got rid of the bicep force, found the elbow force, and then we would have used again sum of forces in the y direction to find the bicep force. Now, I said when we started this problem that if we did not know the direction of the elbow force and the bicep force, that we could just sort of guess what they are, and if we just pick a direction there, and if we, when solving this, if we found that the bicep force was a negative force, if we found that the force of the bicep were negative here, it would simply suggest that we drew it the wrong direction. So it would mean that it actually goes down here, which then we could have redrawn it before we did the sum of forces in the y direction, but or we could have left it in there as a negative value and calculated the elbow force by putting it in here as well. So it means the same thing as previously when we did sum of forces in the x and y directions. If we weren't sure of the direction, we could pick a direction, and if we end up getting a negative value when we solve for it, it just means that we drew it the opposite direction of which it should have been.